All right, welcome to your next 222 lecture. And in this lecture, we're going to talk about hashes and hashing and hash tables. Um, and this is all related to a data structure for storing and retrieving information efficiently. And so the idea is we have a bunch of data and we want to, ingest it in a program and store it somewhere in memory. And then we want to be able to search for pieces of information or retrieve a piece of information possibly linked with some other information that's stored with it. And we already have a number of ways we can do this. We could take this information, we could just store it in an array, one piece after another. We could put it into a linked list, which, unlike an array, can grow until we run out of memory. We could push it on a stack. We could put it into a queue. A hash is a different way of storing information, and it's often associated with something called an associative memory. Or an associative array. And if you remember in 224, when we look at writing scripts in Bash, we play around with associative arrays where we can index arrays with things other than integers. So what's the idea of a hash? It's something that we actually deal with already outside of computer science. For example, we have a dictionary, and it's got a lot of words stored in it, and you want to find out, a definition of a word. You can look it up in the dictionary. The problem is, this dictionary, it has 1,600 pages to it. And, each page will have, I don't know, dozens of words. And so that's a lot of words. How do you find the word you're looking for in all of that information? It's a data structure question. Well, we do something pretty simple but clever with dictionaries. Suppose we want to find the word hash. Well, which of these 1,600 pages should we search in? I don't know, but there's a trick, which is if you look on the side of the dictionary, there's these little tabs keyed by letter. Now, we're looking for the word hash, and we know that begins with the letter H, so we can go to this tab that's got an H on it, and once we get to that page, all of the words with H's on it will be somewhere in this section. Somewhere between that and this tab that begins with J, right? So we've reduced the dictionary to this much skinnier collection of pages, right? From page 626 to 750. Well, that's only, 124 pages instead of 1,600. Well, we still have to find the word here, but this is alphabetized. And so if we're looking for HAS, we just flip through until we find HAS up here. And we can come down here and there's the word hash: to chop or mince, to chop into small pieces, to make a mess of, botch, or bungle, which is exactly what we're going to do in our lecture today. We're going to take our data and we're going to mix it all up and make a mess out of it. But in doing that, we're going to take the problem of searching 1,600 pages of data and reduce it down to searching a much smaller set of data. So this will be an efficient way to search for data. And the efficiency can get pretty extreme. If we do a theoretically perfect hash, it's actually going to be order 1. And remember, order 1 means that no matter how much data we have, it takes the same amount of time to retrieve a piece of information. So whether we have 10 or 100 or 10 billion things stored in our hash table, we can search for a particular entry, and in a fixed amount of time, we can say whether that entry is stored or not. And that's pretty magical. So that's a theoretical, but we'll get pretty close to that theoretical performance. All right, so how does this work? Well, basically, what we did with the dictionary was we took a word like, HASH, and we said, let's look in only one section of our data. And we chose that section by just picking off the first letter. And we said, okay, we'll look in the section in which we have letters, words stored that begin with the letter H. We can do the same thing with other kinds of data. So imagine, for example, if you wanted to take a word and we put it into this box, And what comes out is a letter, which is the letter A through Z, which is just going to be the first character of the word. And now we have a map. We have A, B, C, D, X, Y, Z, and maybe each of these corresponds to an array. And so if I'm looking for a particular word and it begins with a C, I'm going to say, okay, I'm just going to search this array. And it's going to be a lot smaller than if I took all of my data and stored it in a single array. I'm breaking my problem down to a much smaller piece, 1/26th the size. And this is not great, right? Certainly if something starts with a Z, I'm going to have very few words over here. But if it's something that starts with a C, I'm going to have a lot of words that start with a C. But we can extend this idea and start breaking things up into smaller and smaller pieces. Now, an array, might work fine, but in practice, we might actually make each of these things a linked list. And so the way that our hash would work is you take a word, you get the first letter, and you go to one of 26 linked lists. And so here's our first linked list for the letter A. Here's our second linked list for the letter B. And here's our 26th linked list for the letter Z. Now, we could just store our data directly in here in whatever order it happens to get stored, and we could just search each of these, and that's an order n operation. We could try to do something like a binary search if this was an array. Eventually we could make this a binary search tree. But a better way to speed this up is to create more of these lists. To not split into one of 26 linked lists, but maybe one of 10,000 linked lists. Well, how do we do that with words? We could take the ASCII code for the first two letters. So here's a word like HA. And if we use a 7-bit ASCII code, we could take the 7 bits associated with this and the 7 bits associated with this and get a 14-bit number. Well, how many 14-bit numbers do we have? 2 to the 14th, 16,000. And so by looking at the first two characters of our word, we could choose one of 16,000 linked lists that all of our words that begin with an HA will be stored in. Now, we can actually do better than that. We don't actually need 128 different codings for this second letter. If we just think of uppercase letters, there's 26 possibilities for the first letter, 26 for the second. We can multiply those out. That's a little over 600. Right? So by using the first two letters, we could split all possible words into one of, several hundred linked lists. And then those lists would be, relatively small, 1/6 or 700th the size of just storing all our data in a single list. So we're trying to subdivide our data into smaller bins. And there's other things we could do. If we use this approach, there's a problem with that, which is lots of words start with TH. And all of those words that start with TH, they're going to get coded to the same linked list. So that particular linked list is going to be really, really long. And lots of words start with QU. And there's really no words that start with QZ, so there's going to be a linked list that is completely empty. And in fact, I don't think there's any words that start with a ZZ, and so the linked list corresponding to that will be completely empty. So we want to be careful about how we choose this mapping from data we're trying to store to which of our linked list we're going to store it in. And that's really the essence of what makes a good hash function, what lets us get close to that order 1 behavior. So this notion of a hash function, just think of it as a box. We put in data and we get out an index. and then we use that index to select one of our linked lists. And we can make this function, you know, anything that we want, but ideally it'll be something that will split the set of data we expect to work with evenly into however many linked lists or buckets we decide to map into. So one thing we might do is we might say f of some string equals, let's just add up each of the characters up to the null terminator of our string. Let's just add up its ASCII code. And then let's take all of that and let's reduce it modulo 500. So add up all the ASCII codes through your entire string of your word, divide by 500, see what the remainder is. That will give you a number between 0 and 499. So one of 500 indices. And then, you know, if this gives us a 37, we just go to the 37th linked list and we tack this word into the beginning. And theoretically, if you had 10,000 words you were storing, each list would have, you know, maybe 20 words in it. And searching a list of 20 words doesn't take that long. Average of 10 operations, worst case 20, best case 1. But a whole lot better than 10,000, right? So this is a hash function, right? It's something that takes data and maps it to an index. And if we use that index to map to a linked list, this is something that we call chaining. And the idea is once we hash your data, we get a particular chain of data and we just, you know, tack the new piece of data onto that chain at the beginning or the end. And so that's really all there is to a basic hash table, right? It's this thing that we put in data and it takes us to, you know, a linked list where we can search for that data. And typically we're using this with this idea of association. So for example, maybe we want to store a set of information with a name and a phone number. And so we're going to store Nick, and their number is 202-555-1212. And we're going to star Phil, and Phil's number is 415-888-1111. And so on. And what we want to store is not just a list of names, but names and associated phone numbers. So the idea is we take the names and we run them through a hash function. We map it to an index of a linked list, and then in that linked list we store pairs of information. So our linked list would look like name, number, and then a pointer to the next node in the linked list. And there's a name and a number and a pointer to the next node in the linked list, and so on. So if you have a name and you want to know what the phone number is corresponding to it, what do? You take the name, you run it through your hash function, you get an index, you go to the linked list with that index, and now you start searching node by node for the name you're looking for. Now you may find the name you're looking for, you may find other names that also hashed to that same index, so you check, that's not the name, oh, here's the name, and there's their number. So this is exactly the same setup as an associative array. Remember, with an associative array, like in Bash when we say declare -i, we have an array, let's call it data, and we can search for an element with a certain index, but this index doesn't just have to be an integer. It could be a string, it could be a collection of words, it could be anything that we want. And so an associative array for storing names and phone numbers, we could say, you know, data bracket Nick equals 202-555-1212. data bracket fill equals, and we could store Phil's phone number and so on. And so when we want to find, hey, what's Nick's phone number, all we do is we go into our array, say, give me the element with that index, and there's the number, right? So we make that work by using a hash table. And the underlying mechanism is this name Nick first goes through a hash function, comes up with an index which points us to a hopefully short list, a linked list in this case, and then we search every node for the name that the person asked for, and if we find it, we give them back the number that's stored with that. And associative arrays are really powerful. Being able to access data with non-integer, non-consecutive indices is a really powerful feature. For example, if you were writing a compiler and you wanted to build a symbol table, you could make an array where each variable was used to index the address where that variable was going to be stored in memory, or information about what type of variable it was, or what its initialization value was, and so on. So, so these are powerful mechanisms. What we're working on today is sort of how these things are implemented. And so this idea of a hash function is going to be one key, and the practice problems will mostly give you some experience playing around with hash functions. And a good hash function gets you really good performance, best case possible, order 1. A poor hash function, you can end up with, order n performance, where if you have n pieces of data, it takes you n operations. So this is an implementation using chaining, and that's a pretty common way to build this because, the entries can grow more or less without bounds unless you run out of memory. But sometimes we want to implement a hash table or an associative array using a conventional array. And so we might have, just a plain old array. I'll call it hash. And let's just imagine it's an array of 100 entries. And so we're going to take some data, and we're going to run it through our hash function, and we get an index 0 through 99. And so if we hash our piece of data and it comes up with an index of 42, we're going to store our data right here. And now when you want to look for your piece of data, you run it through the hash, you get a 42, you go into your array, index 42, there's your data. Right? That's nice order 1 performance. The problem, of course, is what happens if two things hash to the same location. You get what's called a collision. So what we do is we make our hash function able to take in two numbers. There's the data that we're feeding in, and then there's something we'll call a probe number. And our probe number always starts at 0. So we put in a probe number of 0, we put in our data, we hash it, we get a 42. If 42 is already in use, we can't store our data there. So now we rehash, but this time we put in a probe number of 1. And this function should give us a different number. And maybe it gives us the number 13. And so if 13 is free, we'll store our data there. Now we're losing some efficiency, right? Because we might have had to do 2 operations to store our piece of data because the hash function took us to a location where we had a collision. So we might have to hash twice, or 3 times, or 4 times. So our performance starts to go down. This is exactly the same thing as when we hash to an index where there's a linked list that already has a lot of data in it, and we want to search that for something. It's going to take us longer. So this is a different approach to chaining, to using linked list. We just have an array, but we can change where our hash function tells us to store data in our array. So if we hash our function, it comes to a 42, and that's already in use. We set the probe to 1, hash again, and tells us, okay, we can store our data in 13. And if we hash another piece of data, maybe that'll hash to 99, so we can store some piece of data there. But maybe we get another piece of data, and we hash, and it comes back to 42. And so we'll hash again with a different probe number, and maybe that'll hash to, 51, and so we'll store our data in location 51. So this is, the name hash. It's turning this data into a nice big mess, chopping it up into little pieces, scattering it all around, tossing it in the pan, mixing it all together. So using this approach, this is called probing. We need a more sophisticated hash function that can take in a probe number. And if our second attempt to store generated a collision, if this element 51 was already in use, we would hash again with a probe number of 2. And that would be our third attempt, and that might give us a different index that's available. So this is an approach to handling collisions called probing, right? When we use linked lists and we just keep tacking onto the list, that's called chaining. This is called probing. And so probing makes things a little more complicated. When you want to search, we take our data, we hash it, say it hashes to a 42, we look here to see if our data is stored. If it's not stored there, we're not ready to say the data is not in our hash table. Because it's possible that when we stored our data, we found a collision here, and so we're going to want to rehash with a probe of 1, and if that takes us to 13, we'll check location 13, and maybe we'll find our data there. So searching is more complex, but it gets even more complex when we have deletions. So imagine this. F of, let's say I want to store the word cat with a probe value of 0, and let's say that's 42. So I store a cat here. And let's say I want to hash a dog, and that comes down to location 42. Well, I can't store a dog here because 42 is in use, so I'm going to rehash. And let's say that gives me 13, and 13 is available, so I'll store my dog right here. Alright, so if I search for a cat, what do? I hash cat 42, look at 42, there's the cat. Yep, that's in our data. I look for a dog, I hash dog, I get location 42, I look, dog's not there, but something else is there. I might have gotten a collision when I store a dog. Let's rehash. Rehash with a probe of 1, get a 13, yep, there's my dog. Now let's say I try to look for a book, and let's suppose that happens to hash to a 42. Alright, so I look for a book, I hash with a probe of 0, I get 42. Well, if it's not there, but something else is there, there could have been a collision. So let's rehash. So I'll rehash, and let's suppose this comes up with a 2. So I look in location 2, and location 2 is empty. Now I can say, nope, the book's not stored in my hash table. Right? Now if there was something else stored here, it's possible I got a collision when I tried to store, and I would have to rehash with a probe of 2. But this is where deletion gets complex. Suppose I try to delete the cat from the table. Well, if I delete this and I mark this empty, what happens when I search for a dog? I hash a dog, probe is 0, I get a 42, I look at 42, that's empty, I'm going to say there's no dog. So I need to know that cat is not stored in here anymore, but I need to know that there was something stored there, and that might have caused a collision. And so if I find that that's not the dog I'm looking for, I still have to rehash, get my index of 13, check location 13, find the dog right there. So you'll get to play with some of these complications in a programming assignment. And they're not bad, but it's a lot to keep track of. But once you code it, it becomes a lot more clear how all of these details work together. And in the end, our hash table ends up looking something like this. So here's our array. And there's indexes. So if there's n elements, last index is n minus 1. And so we might have some piece of data, which we can call a key. So if we're using this to store something like phone numbers that are associated with names. This would be our key. This would be our data. And so you would have a key data pair. But we also need some other information. We need to know, is our hash empty? So let's have a flag saying in use. And we'll initialize this to 0. And if we hash and we come down and in use is 0, then we know that cell is available. If we're trying to store something, we can store it. If we're searching for something, we know it's not there. Because remember, nothing is actually empty. We can't actually delete everything from this element of an array. Every element of an array always contains something. So we would have a flag saying this is in use. And we also want a flag saying deleted. Was there something in there that got removed? Because if there is, we need to know that so that even if the cell's not in use anymore, we know that we should keep reprobing when we search for things. So our hash table will actually be an array of structures containing these pieces. And what kind of thing is key and data? Who knows, right? Could be names and phone numbers, could be a pair of strings, could be a set of numbers, could be some binary key and a WAV file, right? All sorts of possibilities, but inside the structure that we make an array of for our hash table, right, we've got a key data pair and then some flags for housekeeping. And then we have some hash function, and we call it hash func, which takes in a key and a probe number and returns an integer. And that integer tells you which element of this hash table should we look at. So setting this up is really not that bad. It's a lot of parts and pieces, but once you start putting them together, it starts to make more sense. So two fundamentally different ways of dealing with collisions, with things hashing to the same index. With chaining, we're just making linked lists. With probing, we've got an array. And if we find a collision, we reprobe and rehash with a different probe and find a different spot in the array to use. So an advantage of this is, our list can grow without bounds until we run out of memory. But, if we've only got 10 linked lists and we've got 1 billion pieces of data, that's 100 million pieces per linked list. That's not very efficient. So periodically, we would like to rehash where we would say, 10 linked lists is not enough. Let's restore our data in a bigger hash that has 50 linked lists. And we could go through and we could take all the data one by one and rehash it and distribute it among 50 linked lists, and now our lists will be, quite a bit smaller than our original 10 linked lists. When we use probing and we're storing our data in a hash, we will run out of space once we've stored n pieces of data. And in fact, even before we've got n pieces of data in here, we're going to find cases where we try to store something, we might have to rehash, several times before we find an empty spot. So as this table becomes more and more full, our efficiency will drop. So there's a notion of load factor, which is how full the array is. And typically when you implement a hash table, you can specify, hey, when the load factor hits, 35%, let's rehash. Let's make this table bigger, restore our things so that there's more space. So we like to have a lot of space in here. The more space you have available, the more efficient your hashing is going to be. What else should you know about? You should know about clustering. And inevitably, if you have enough data, you're going to start reaching collisions. But with a poorly designed hash function, what you may find is that in your hash table, you have a lot of data stored here, and a lot of data stored here, and maybe a lot of data stored here, and then you have a lot of empty space. Instead of distributing this data nicely throughout the entire hash table. And that's a consequence of your choice of hash function and the nature of your data. And so if you understand the nature of your data, you can choose a hash function that will avoid clustering. And I'll give you an example. If we used student IDs, right? Most student IDs start with 201. And so if we just chose the first 3 digits to index one of 1,000 linked lists, right? Well, there would be one linked list 201, that had every student ID in it, and all the other linked lists would be empty. But if we chose to use the next set of 3 digits, we would probably get a more evenly distributed set of data among the linked lists. Even better might be something like, adding up the digits multiplied by some scale factor for each one, and then reducing that sum modulo 1,000. That might give us a nice, really evenly distributed set of 1,000 lists containing our data. So understanding the nature of your data can make a big difference in terms of choosing a hash function. All right, so that's the basic mechanics of hash tables and associative arrays. And we'll get some practice implementing these. All right, so that's the basic overview of hash tables. Main thing to keep in mind, hash tables are associative memories. They work like associative arrays. We have a key that you use to access your data, and basically we want to go into this data structure with a key, pull back a piece of data. And so as an abstract data type, our interface might be something like, some sort of initialize function, and then typically something like put. So we can say put a key data pair, and then something like get a key, and that returns a data pair. And maybe we'd have a search function. But do we really need a search function if we already have a get function, right? We could just say, hey, get me the data associated with this key, and we'd have it return, I don't know, maybe null, or some, particular value if the data doesn't exist. So we could use that as a search. So it's mostly put and get. And when we use hash tables in 223 in Java, right, we'll create structures and we'll see put and get routines for accessing them. So think about key data pairs. Implementation wise, we can implement with chaining, where we use our hash function to pick one of a number of linked lists, or with probing, where we use our hash function to pick an index, and if we get a collision, we rehash multiple times. So our hash function takes a probe value or an attempt number, and we can use that to eventually find a spot in our array where we can store our data. And the other concept was this notion of load factor, which says how full is our array. And so we can say if our array gets beyond a certain percentage full, let's rehash and make the array bigger, put things into their new locations, and have more empty space available. So the last concept I want to talk about is the idea of an iterator. And we touch on this in 224 when we talk about associative arrays. But this is a bigger topic that will come up in various data structures we're going to work with. And this comes out of the idea of an associative array as an array that we can index with something other than an integer. So I could have an array called data, I can index it with Nick or Phil or something else, instead of just integers starting from 0. Well, that's a very useful, powerful thing to be able to do, but it raises a complication, which is, what if I wanted to go through my array and look at all of the information inside the array? Now, if we have a plain old array, it's pretty simple. We can just say for I equals 0 to n, print data bracket I. And if we have n plus 1 pieces of information in our array, this would print them. But that works only because we know that our array is indexed with integers starting from 0 and going up by 1. But if we have an array that's indexed by, strings, we can't ask for, the element associated with every possible string, because there's an infinite number of possible strings. So how are we going to retrieve the data from our array if we don't know all the indices. So we use an iterator. And an iterator might be something like this. Get first, and this returns us a key. And then we could say get next, and this returns us a key. Alright, so what does this do? When we say get first, we get a key back. We don't know which key it's going to be. You know, it could be the key that's sitting right here, but probably not. But it's going to be some key somewhere in our hash, right? So something that we've stored at some point. And then each time we call get next, we will get a different unique key. So we call this repeatedly. And each time we call this, we get another unique key. And we can use each of those keys to access data from our hash. So if we had stored data under cat and dog and book, we could say get first, and maybe get first would give us dog. And then when we call get next, maybe that would give us cat. When we call get next again, maybe that would give us book. And we could set it up so that it returns null when there are no more keys left to be retrieved. So this is an iterator. It's a way to go through our set of keys one at a time and have them given to us in no particular order, right? And iterators rarely make any promises about the order in which they'll deliver data, but they do promise to deliver each piece of data exactly once. So we won't see the same key twice. We won't see a case where we don't get a particular key. This will give us one key, and this will give us all the remaining keys each time we call it. And so if we wanted to print out the contents of our hash table, we could do something like, you know, key equals get first. And then we could say while key is not equal to null, data equals, and we could use our get routine. We could say let's get a piece of data, and we could print out data equals data, key equals key, and then we could say key equals get next, and we put all of this in a while loop. Alright, let's get the first key as long as it's not null, get the corresponding piece of data, print out the data key pair, and then get the next key as long as that's not null, get the corresponding data, and loop through here until get next tells us there's no more keys. This will give us a print of all the data key pairs in our hash table. So you always want some kind of iterator, and that's going to be part of our abstract data type. So the full ADT would be, you know, some kind of initialization, put and get, and then something for iterating across the keys. Alright, that's a high-level view of hash tables. We'll dig deeper into that in one of the programming assignments. And the practice problems, like I say, you're largely going to deal with hash functions and looking at collisions and seeing how these things behave on different sets of data. Alright, have a good one. Thanks.